Thanks, Cassidy. Good morning, everyone. So our plan for today is diving more into our, quantum circuit operator, focusing more on, some named operators, named circuits, do some, the problem solving, and then we are going to have a sort of, free discussions on a few interesting features of our framework that we would like to share with you guys. So again, a reminder, whenever you think about, a quantum circuit, remember it's a composition of, operators. And what I would like you to remember is that you can see this composition in the usual sense when we say composition in everyday life, and also composition in Wolfram way. Composition had a very specific meaning in Wolfram language. So that's both of them together. For example, Nick, you can show one example of composition of two functions, three functions. And you see, it's like a series of and you see H, acts on X and then G and then F. So that's the same approach. And of course, the common convention that we have in the literature. So it's gonna be the right composition of so let's just show right composition too in case. So you see, it's like the one that you put on the left side, F, it acts first, then G, and then H. So right composition is the your thing to remember, whenever you are thinking about our circuit operator. So one approach is giving them a series of operators. The other approach is going with the named operators. And remember, most of the time, people, they are interested to apply a quantum circuit operator on a register state. So you don't need to bother defining your register state. If you just acted on an empty bracket, we would understand it you are acting that on a register state, and we do all the computation behind the scene. So either you can give this state explicitly, or if you don't specify the state, we would treat it as a register state. Okay. Let's go through some of our name operators. In our framework, we have a collection of named circuits. And that's one thing that you have to be very careful. In our name circuits, are different from name operators. So this is the Bell circuit. Of course, the result is Bell state. This is the the usual magic. What you see here is the application. Now we have magic. So S Toffoli state, that's the common decomposition of Toffoli, gate. Fourier, and then for Fourier, remember, you can specify the number of qubits. By default is 2, but you can add more qubits. For example, the next one is 5. Fourier, quantum Fourier transform is a very common circuit that has lots of application. The most famous one is in phase estimation.
Maybe we can show that it's equivalent quantum operator, same as just quantum operator. But in yes, for 2 qubits.
This is the equivalency of the two. One other argument in the Fourier transform that is interesting is that, let's say that for example, you have a Fourier circuit on 5 qubit, but you would like to shift it down. For example, you would say let's apply that starting from, for example, third, and then it shifted to the third. So it means initially it's going to apply on basically 4th qubit. Let's look at the diagram, and you see here now we shift it down, and it starts with 4th qubit. So that third argument also helps you to position it wherever you want. as we said, quantum Fourier transform has lots of application. By the way, we also have inverse of that. So let's also show the inverse in case. So you see, it's exactly the same thing, literally the inverse, so you can also go with the inverse. What else? By the way, for a circuit, one interesting feature is that, you can also ask for, the inverse directly. For example, you can have your Fourier, and then on Fourier, you can directly ask for the inverse.
Is it inverse? I think it's dagger.
Yep. So you see, it's what is interesting, is that let's see, they are exactly the same. I don't know, some people they prefer going working directly with the inverse. Some people they prefer to see it in this way. So remember, dagger was a feature that we had for states, for operators, a property for all of them, also for the circuits, and exactly the usual meaning that it has, in quantum. As said, quantum Fourier transform is a very popular circuit. The most important application is in the phase estimation. So for the phase estimation, we have basically two other arguments besides specifying the name of your operator. So this is the phase estimation. So the first argument is a unitary operator that you are interested to find some specific feature of its eigenfunctions. And then the second argument, you're saying that how many steps. So for your estimation, the precision, the accuracy of your estimation depends on the number of steps. So this is the case with 3. You can add, increase it more, and your estimation will be a better estimation.
No, it's not. Shit.
And it gets more and more complicated. Of course, as you increase the number of qubits, your estimation for the corresponding phase of that unitary operator will be a better estimation. Okay, so there are also some textbook, Bernstein Vazirani BV, circuit. So here, the main purpose of this circuit is finding a circuit string that's and usually some of this let's apply it on a register state, and let's look at the probabilities. You see here we are saying that the secret string is 101, and you see in our measurement results that's exactly the result that we get. Okay, for all of most of these, not all of them, for most of these named circuits, we also have the corresponding oracle. So the oracle is usually the name you would see, in the Grover, we also have it. The name of that basically circuit followed by the oracle at the end. So that's basically, how you can get the corresponding oracle. Let's look at the questions. There has been some issues with the notes. So Cassidy, if you can just, refer them to the right link for today's notebook, that'd be helpful. Victor, he has a question. Is it all applicable to the irreducible tensor operators? Not sure. I'm not sure if I understand the question. It referring to what? So that part I do not understand. Definitely, irreducible tensors. We use all over. As said, behind the scene, everything is tensor for us. But I'm not. Nick, do you have any comment on that? Maybe.
Yeah,
Max,
I'm not
the
sure what
the
it means.
the issue, I'm so sorry. The issue with that notebook is that the one that you gave yesterday, that published operators one, people don't have permissions to it.
I have uploaded, so my bad. Sorry about that, guys. I made a mistake, and I copy and paste the wrong URL. So it's on the community. So Cassidy has already shared the link for the community. So if you just go there, you can find the right link to that. So it's already, let me just find it very quick. Let me just copy and paste it. This is what happens when you copy and paste very fast. When I did it yesterday, let me just find it. Give me a sec.
Is it the one about operators
Yep.
on measurement?
The one that you get. I made the same mistake. Like, you remember that one.
This one, right? I posted it into chat.
Yes, thank you, Nick. So that's the one that you can get it. And Sid will do that. Like, all of them, like, we also, like, put it on cloud. So Nick, would you like to comment on that, that question by Victor?
About irreducible, I'm not sure, because all our tensors are just tensors. How would you act on the irreducible? In what sense they would be represented as irreducible tensors? So like if you make an operator or a state, it's just a tensor. It's like I don't quite understand.
So basically, like the Victor, tensor is basically behind the scene. Everything for us is a tensor, like, but not sure, like, so let's move on. If you can, elaborate more on your question, we'd be able to answer that. So those of you who are familiar with, like, there are two kind of famous approaches to do quantum computation. One of them is the usual gate approach, which is what we discuss almost all the examples. Yeah, all the examples that we have shown you so far, it was a gate-based approach. Another approach is measurement approach. Okay, they usually called measurement, like, based quantum computing. For those approaches, there is very famous, like, a very entangled famous states that they use. That the state is called graph states. So the corresponding circuit, so let's say that, you have this graph, and then the corresponding operator means whenever there is an edge, apply is, control Z between, like, the corresponding, like, vertexes. For example, you see between 1 and 2 there is an edge, so we are applying is, a control Z between 1 and 2. Between the vertexes 1 and 3, likewise 1 and 4. So that's the corresponding, basically, graph circuit. And remember, we also have, a state called, graph state, that also a named, a graph that we have. And you can easily show that, like, the relationship between the two is like this. If you apply a collection of Hadamard on the top of this, graph states, the result of that, circuit on a register state is exactly the same as our graph state. So basically, like, in other words, like, remember, like, this is what we discussed last time. A series of Hadamard, Nick, let's show them the diagram, they would see it better. So you see those initial Hadamard. Always when you see a collection of Hadamard on your qubit, it means prepare a uniform quantum superposition. So in some literature, they include that piece into the circuit with the Hadamard. In some literature, they drop that. So just be careful when you're reading the literature. Like, some people, they always start with the register state, all the qubits in 0 state. Some others, like, they include some initial preparation. You can kind of, like, include it into your circuit. There is a question about time evolution. We'll come back to that question, D. Like, we will discuss about it after we are done with the circuit operator. Okay, a very famous family of, quantum search is, like, basically Grover. So for the Grover, you have to go, sorry about back. Just give me a sec. Sorry about that. So what we have here is that, like, your Grover, the circuit, and a Boolean function. So the main purpose of, like, Grover algorithm is to find the solution of that very particular Boolean function. Okay, and Grover can have many different oracles. One famous one that you see here, people call it Boolean oracle. So the idea of Boolean oracle is that given your basically like the number of qubits, or basically the number of elements that you have in your Boolean function, you see here is 4. You add one ancillary qubit because you would like to save the solution. So you see here, it has only 4 variables. So the idea of Boolean oracle is to save the solution in an ancillary qubit. Okay, for example, let's just explore it using different functionalities in Wolfram language. For example, we can find all the solutions for that Boolean function. Okay, the last comment, the replacement that you see at the end, is just replacing true and false, like to 1 and 0. So these are all the solutions for that very particular Boolean function. Now what we can do, we can prepare like these quantum states, and of course the ancillary qubit in the ground state 0. So this is the collection of states that we expect them to be the solution of that Boolean function. Okay, now if we apply the Boolean oracle on all of those states, now let's look at just show them the traditional form. You see, for all of them, the last qubit is switched from 0 to 1. So basically, like that's how we save basically the solution of a Boolean oracle on the top of our ancillary qubit. And of course, this is not the end of like Nick, if you scroll up, show the Grover one more time. So that's just a Boolean. And then the next step is the amplification. Basically, like, you amplify that amplitude in a way that, like, after a series of, like, Grover algorithm, you can increase, kind of maximizing the amplitude for the solution. And if you do the measurement, that's the solution that you will get with the highest probability.
Have it separately, right?
Amplification.
Diffusion or amplification?
Both of either amplification. So that's the part that you can also get it directly. So here, like so for Grover, there are let's discuss about all the details that you can have in Grover. So one thing about Grover is that it has 2 parts: your oracle amplification. Okay, you can extract both of them. You see here, like this is the diffusion part. It is also called amplification. Both of them, we support that. One other thing is that, remember, whenever you have a sandwich of 2 Pauli X not around the control 1, it is the same as control 0. Okay, you see that, like that yellow part of Grover amplification part. That's why in some textbook, instead of like control 1, they show you control 0. Okay, and we also have it in our framework. So the only difference, remember, like they are exactly the same. In the top one, it's control 1. Now here is control 0. And we also have all of them in our, for example, for the amplification, we also have amplification 0 or diffusion 0. Like we can also add it there. So it's just like the different conventions, but remember, like the operation is exactly the same. Whenever, like one more time, it's an interesting feature when you have 2 NOT. Remember, like NOT gate and Pauli X, they are the same. So when you have 2 of them sandwiching on a control 1, it's like doing control 0. One other thing, like let's go down, scroll down. Yeah. So this is one potential oracle for Grover search algorithm. So we save the solution in another, ancillary qubit. Another approach that is called phase oracle. What's happening here is that this time we are saving the solutions in an overall phase of all those qubits. For example, this time, like let's prepare. So this time there is no ancillary qubit. So let's prepare our states, like again the solutions of the same Boolean functions. And this time, if we apply the phase oracle, you see this time the solution is in the phase of that state. Okay, and by the way, since we have a superposition of many states, this phase here is observable. Okay, it's because the phase is added only to the solutions, not to the overall state of your quantum system. So whenever you're looking at different Grover search algorithm in the literature, just pay attention if they are working with yeah, that's actually a very good example. So you see here those that are solutions, you see there is a phase negative. It's like having a flipping the phase in front of them. So you see those that are not solution, it remains as positive. And of course, in the next step, when we apply, the Grover, you would amplify, that those states. And by the way, remember the effect of, Grover is it's an oscillatory behavior. So after a few steps, you would maximize it. But if you keep doing that, it minimizes, that effect. If you want more information, let me just find it. If you go to the community and under my name, I have added a series of examples. Let me just put it in the chat here. So in that community post, you can find many different examples of the Grover applied on your quantum set. It's this step of repeating Grover, it's a little bit tricky, how we should do that, which part is the nested part, because you just need to Nick, the tricky part is there is a not operator on the ancillary qubit, and then keep doing that. So that
No, I think you have to also apply the oracle.
yes
again.
And applying oracle again. And then there is also an analytical formula which is called Grover probability of success. If you look at that community post, you can easily see that that analytical formula and the numeric that you get out of the simulation, they match perfectly. They are the same thing. Grover is a very popular search algorithm, so you guys can explore it and see all this interesting feature. But again, remember when we talk about that's the part that when in the literature, whenever you see a repetition, iteration of any algorithm, it's very important to understand which part is repeated. Is it only the diffusion part, or including the oracle? That's a tricky part. I'm sure you guys can explore it on your own. What else for our named up circuits, Nick? Is there any interesting feature that you would like to add for the named circuits?
Let's see. Maybe I haven't tried it in a while. If I actually have it controlled and then act on it on another circuit, like bell, for example. It's fired the same. Not quite.
This is actually last night I was also thinking about that. It's it's right now it's broken, but we can revise it quickly today and making sure it's working. So basically what Nick is telling you is that you can have a named circuit, and then you can have that named circuit in a controlled manner.
Yes, because a quantum circuit bell already fixed to the first and second one. I can't control it on the first one, so I have to pick something else.
And by the way, what is not nice right now is let me be clear. Show the diagram. So this diagram, what we are gonna do would be like this. So and this is the part that it just needs a little bit of coding. I think today Nick can easily take care of that. It's much nicer if we put the whole bell in a box. So as of now, it's we are expanding that in a not very trivial way. This circuit is kind of, at least the diagram is non-trivial. Okay,
Yeah.
but so what we are gonna do, we are gonna keep, like, at least for the sake of diagram, we are gonna keep the named circuit inside the box, and then, like, control and everything that you have, like, it's gonna, yeah, that box, we will keep it, as it is, and then you're gonna have, like, these are the boxes that I meant, and you are gonna have your control, and then you would see the whole box. As of now, you don't see it. That's why, like, it's not very nice. And by the way, like, you see, like, look at the notation that we have for the magic state. You see, like, that label on the top. It's literally a quantum, a Wolfram composition. You see, it tells you, like, you have a tensor product of S, then you have Hadamard, and then you have C naught. Okay, so, like, that's the composition that we have. And let's just comment, because this composition is an interesting feature. For the composition and a circuit, what is interesting is that you can directly do the composition with operator. For example, Nick, add quantum measurement, which is, like, it's not a circuit, but, like, it's a sort of, operation, and you see, like, we understand, what's happening here, and the result is a circuit. So, like, we are just, saying that, like, okay, like, at the very end, apply, like, your measurement, or any other operator, like, it could have, I don't know, another Hadamard at the beginning. uh One comment, like, just, whenever you're using that, like, pay attention to, like, the usual composition. It's not called, like, left composition, it is called just composition, and the right composition that we have, like, so for composition we have, two syntaxes. If you use, at and, star, like, the order would be different, like, one of them is, like, applied on the right side, the other one by convention is always to the left side. So just whenever I'm sure you are familiar with the syntaxes, but in case, just pay attention. So this time, like, that poly X. So you see, it acts at the very end. So this is why it is called right composition. Okay, so
This is the left composition.
left composition. Sorry,
This is right.
left. This is right composition. Yeah. What else? By the way, you can also do it with the circuits. Like, let's just show, like, two circuits, composition of two circuits, like, as they like. So you can also do the composition of, different circuits. The composition of, different circuits, it will come very handy when you're doing, variational, like, circuits, using our framework, because, like, you're applying a series of, like, similar circuits on your quantum systems. What other interesting features for the circuit?
Oh, I don't know. Compiling it. Well, we already showed it.
Oh, do you want to comment on different way of, like, different methods of calculation?
Yeah, why not? It's by default, we already showed previously that it's a basically tensor network contraction in order to compute this quantum operator, or whenever you acted on a empty register state or measure it, you just contracting this tensor network with some pre-filled tensors, basically. But there's some, but because we already support like basic composition of operators, which is just multiplying producting tensors together, right? Like you usually do, like this. You can apply this to another operator, right? You can just do it for the circuit instead of just doing something efficient like contracting tensors all at once in some fancy algorithm. It's basically a different method to this property that computes an operator, it's a Schrödinger method when
Yeah.
you just compose those, right? And the same kind of method goes for when you apply it to a state or to an empty register like this. We also have keyskip method. Hopefully it works, but it's gonna be dangerous. But let's see. Basically, underneath it's gonna compile it to a keyskit one, run it through the using keyskit and convert back to a state.
Yeah.
Right. And
So
the result is gonna be numeric at least. So as a result, because it can do symbolic and exact numbers. Now it's
for the keyskit, always numeric. Remember, guys, it's.
And we also have another additional backend if you wanna.
Quest.
You have Quest, but you have to do some magic before that.
Quest, those of you it's a very interesting package developed by one of our summer school alumni. He already got his PhD, I believe, from University of Oxford. And what they do, they go to C and they do their computation there, and then they come back here. So for some numerics, Quest can be very fast.
For big circuits, and it usually better works for bigger circuits, more deeper and more wider ones. It's much better than the other methods that we have.
So there are some questions I took a quick look at the list of those names. Many of them, almost all of them are there, but for some of them we have some generic designs. Like for example, we have this big generic rotation. So for example, the Ising type of interaction, you can easily create it with rotation. So we do not have a very specific name only for that very particular one, but we have some generic ones that you can create that. A few of them, there is not a sort of agreement in the literature, how they should be called. Some of them, for example, we already discussed about magic. It's a very popular one. There is a sort of agreement that it is called magic, but for some, it's not a convention there, and that's why we haven't included them. One thing that we didn't show is we have some decomposition feature for our operators. For example, we have the usual ZYZ decomposition. So let's just generate a random operator, show the decomposition, which represents basically a circuit. So basically, what you see here, the first one is any unitary, you can decompose it as a series of the phase multiply, but what usually called in the literature U-tree, which is basically a composition of 3 rotation, and that's the decomposition that you can find for any operator. Remember, this decomposition returns a circuit, so the result is a circuit. There is another question by Douglas. I guess Nick has already commented that on the community, from our framework to Qiskit is it's included in our framework. The reverse, Nick, would you like to again please refer to that community post for more detail. But Nick,
compose it back to a list of quantum operators.
Yeah.
Well, if you already have a circuit, you made it somehow from the Qiskit. It could be any circuit. That's just, it's already a list of operators by definition. Right? So I guess that was the question.
So I guess the question, maybe Douglas, you meant something from Qiskit, a Qiskit object, into our framework. I guess his question is mostly about that
one. Well, I think he's asking if you already make a quantum circuit from the Qiskit one, how you decompose it in the list of quantum operators. But if making it from what I showed in the community post, think this notebook, right? You can, you don't see it. Hold on.
Yeah.
Let me share. Like in this notebook, if you configured your Qiskit environment and you can use Python language cell here, you can just use it to construct your Qiskit circuit inside of it, and then just use a Wolfram client and make a Qiskit circuit object out of it, like this one. And hopefully, we just try it.
Remember, like, one thing about Qiskit is it is in Python, so that's why, like, you need, external evaluate to deal with that.
I'm not sure whether it works now or not as an object itself, because ideally you can basically use it similar to the quantum circuit in the framework. You can apply it to states, right? You can make it into a quantum operator. Let's see whether it works. Oh, it doesn't work for measurements, I guess. Let me comment it out. If you have this kind of without, then it works. And you can apply it to states, but also doesn't work for some reason. But ideally it works sometimes.
So that part, like, using the usual, like, thing is that, the communication with Qiskit, like, from our framework to Qiskit is very straightforward. The reverse, maybe it needs some massaging. Okay. Like,
well, at least you can convert it to a circuit that works a little better, but using the Qiskit circuit object itself, maybe not.
Yeah. By the way, like, yeah, Douglas, like, let's just be clear, like, what Nick was trying to show is, like, just stay at the level of Qiskit and do everything with Qiskit. You can easily, like, given a Qiskit, you can get it, bring it to our framework, and then do everything using our framework. And I think, like, this is honestly, we believe we already have, enough functionalities for those who wants to, bring their Qiskit circuits into our framework. So we don't need to support everything done Qiskit way. So that's the best way. Given you look at the top one, like, your Qiskit, circuit object, just get it, in our framework, which is the quantum circuit property of that one, and then do the rest of computation using that Wolfram quantum circuit. That's the best strategy. Because if you want to, like, basically it doesn't make sense, like, from the very beginning till the end, if you want to be in Qiskit, so it means work with Qiskit, not this framework. Okay. Any other interesting feature about, like, oh, by the way, like, another, let me also put it in the Zoom chat. There is a very recent, big development on all the fancy visualization that you can do with our, let me just find the link. There are tons of different, options. Let me just copy and paste it here. I'm putting that in the chat. So this is the link to our resource, our documentation. There are lots of interesting features that you can do for your circuit diagram. Like, you can change the colors, you can change the background, you can change, like, the sizes. You can add, like, for example, one interesting feature is, like, that I personally like is the connectors. Nick just show them, one option with, connectors. That's an interesting
the diagram, I mean.
diagram. Yep.
So you have a magic one. You can ask for a diagram. It has, is it wire connectors?
Show connectors. I guess show connectors true. Show connectors without I.
There are two versions of those.
Yeah. So basically, like, what is interesting here is that, like, because you may have a big box, okay, like, for example, like, a composite, operator acting on many qubits, and it's not clear for you, like, does it passes through some wires, or does it, acts on some wires? These correct, connectors, like, it helps you to, you see, like, for example, here, this one, it's acting. For example, maybe an interesting case would be, like, for order change the order, and then like yeah, you see like the when it acts on a different situation from those connectors, you can see that okay, so it's acting on this one or on the other one.
Because sometimes it's well, maybe not the quantum. How do you do it? Just recently it become a little bit smarter. So if you do this kind of unitary, because it's a change the label, I guess, just call Q. Use it like this.
Yeah, that's what I meant. Like when you have a big box, and like that big box is acting only on first, third, and the fifth one, you see like you can kind of see that. You see like the wires, this second wire and the fourth wire, they are passing through that big box. But sometimes like it's not very obvious for the people, so those connectors like they can help you to have a better understanding of like how gates are acting. um, uh, I don't know, is there any other interesting feature?
So I don't know. You
Do you have
have
any level example in your mind, like the sub circuits option?
sub-circuit level, yeah, where we had a bunch of circuits like this. Well, I can do it. Have multiple circuits inside of another circuit. It kind of shows them by default in these boxes, right? But you can hide it out because we have, and even those boxes can contain other boxes and so on. And the way you control it is by how much level deep, how deep of a level you want to show your sub circuits. So it's like the lowest one is the 0 one. You can just hide them out like that. Relabel it. If you make a level 1, now they shown completely as a sub boxes like that, outlined.
This leveling, like it's especially when like there's a big box, kind of conventional. Some people they would like to show it, some people they don't want to show it. So like your choice, like how you want to deal with that. So you see like here is quantum Fourier transform, and we just show it as a big box. Especially like it simplifies the representation, because like let's say that like people they know what is quantum Fourier transform, at least nowadays it's a very common thing, and you don't bother showing this detail. So just calling that the usual abbreviation, it helps for the sake of visualization, so you're going to get a smaller representation. Okay, so let's see, any other question, any other comment? Okay, let's do some of those. Those are very simple, but like it's a quick overview of like interesting, important design feature of our quantum circuit operator. Let's go through some of those questions. Let's see the first one. A random unitary only on the qubit number 1. So let's design a circuit with a random unitary. So like what is important there is that like the order. Okay, so you can go with the named. So remember it is a name, and then on the first one it is by default, and then if you change the order it acts on any other qubit. And by the way, like you can have like in case, like let's Nick show the diagram here. So like you see those labels, like you can customize all of them. Like it's your choice. Like how you want to show like uh, those labels. I guess you have to
Okay, that was working.
rapid quantum operator.
Maybe not.
Oh, that's interesting. So
I have to specify ordering. I'll take a look at that. So then this is quiet.
okay, I think like after this session, we are gonna add also that we are gonna support the case, the generic case here, so we can directly apply the label, because having that quantum operator is just an extra headache.
No,
Okay,
maybe you don't have it. You just have to specify how many.
how many?
I
Okay,
think
let's
this
see.
should work. Hopefully.
Yep.
Oh, this one as a second argument.
Mhm. Okay, so let's move on. Like let's have like square root of x on second qubit. Again, like I know these are simple examples, but like just as a practice, like so it has we have different it's, you can call it sx, you can call it v, but like remember each of these building names, what you see as the label, it could be different. For example, if you want to see explicitly if you want to see explicitly like the label is square root of x, so just square root of x on x, that's the best strategy. So like it's either you go with like those definitions that you would like to see exactly like the square root, or the conventional labels. But remember, those labels you can all customize all of them. uh the next one, like let's go a little bit fancy. Let's say that like we would like to have like a depolarization channel with the probability p on the second qubit and the third qubit. So we never discuss about that, but like remember we have quantum channel in our framework, and the way that you can apply it is literally as before. So your quantum channel, let's go with the named channel, which is depolarization, and then specify like where you want to act it. You see like the format, like it's very similar to like that cross the sandwiching that you have, but like you can change it as you like.
And also does some label scrambling, unfortunately.
So a homework for us, like making sure that the labels working fine. Okay, next one, like we have a collection of like the x on 1, z on 2, and y on 3. So remember, in our framework there are many different ways, but as you may remember, like we also, so this is the way that most of the time we discuss about it. But since in the literature people also like poly x string as a gate, Nick also showed the case that you can just give a string as an input for your quantum circuit operator. X, Z, and Y. So we understand it like, as that particular order. This is like, very common, like, poly string is very common. Okay, let's see. the magic circuit, and then measuring both qubits in the computational basis. So this is the composition that we discussed. Like you can have your named circuit and then measurement. I guess we never show it in a circuit diagram. Let's just that's an interesting look. You can have saying it's like do the measurement on 1 and 2 together, and we show like the measurement box, like the big measurement box, or you can say like measurement on qubit number 1, measurement on qubit number 2. The difference here is that like you just see two different boxes for measurements. Remember, these are like two different states, so their measurements are independent from each other.
It also will be different in the actual final measurement if you actually measure something. Because this way you're gonna measure something 4-dimensional because you measure it at once. So your final measured result is 4-dimensional, so it shows it as a have 4 gates. But in this case,
it's see it as like the label 1 and 2.
Yeah, that's going to be different things.
There is a question by Douglas. Yes, we know about that. It's not us. He said, the graphics on cloud. I think Nick, you have a hacky way. State diagram. You remember, like we had this issue with the circuit diagram on cloud too. So, for any diagram, let's just make sure that like we can. Not a for example. No, a state diagram, quantum state 1, and then diagram, the tensor flow diagram of a quantum state. Yeah. Diagram. So this, like on cloud, like right now it shows a black box. It's a cloud bug. You remember, like that graphic bug that we had before on cloud.
Yeah, is it the same?
Yeah, it's the same
right.
thing. Yeah, just the hacky way that we had, like we had to change some options. So let's just change some options so people they can see those diagrams on cloud too.
Yeah, I'm not remember what. What is the fact?
I'll send you the information. Like what was the issue there. So it's Doug. Short answer: we know, like that's a graphic error on cloud. It's not our framework. Okay. The next example, I think, is trivial, but again, like, it's a reminder that, please remember, like, order is your best friend. And, this is example, like, those of you are asking why this sort of examples, like, permutations, like, is a big deal in quantum computing, and like, a series of swap, like, always you can create, a corresponding permutation. So that's why, these are an interesting example. Next one, like, is again, like, a fancy way of order/composition. So we have quantum Fourier transform, not on qubit 1, Nick, 1, 2, 3, 4, all of them. 1 through 4, yeah. And then Fourier,
Weird looking.
okay, then just so you see, like, you may not like it, we totally understand it, but let's create it using the composition. So with the composition,
You mean composition of circuits?
2 circuits, yeah. And let's just kill the order 2, 3, 4, and let's just say 3 and 1, comma Fourier, comma 3 and 1, using that feature. Now they can, yeah, it looks nice.
In this case, it was a single operator.
Yep. Now
So
that's
a single tensor.
Yeah. So that's the whole thing. Like there are some common names, like for example, like Fourier, quantum Fourier transform, or Fourier operator. It's that's how it's been communicated in the literature. Okay, I know it's confusing, but when you are, especially when you are designing a circuit, make sure that you pay attention to similar names. Actually, the only one that comes to my mind is the Fourier transform. Maybe is there more? Maybe there are more, but some of them, some operator, they have a very specific name, especially Fourier, and then you have a big circuit with a very specific name. So when you are like working with circuits and some operators, just be mindful of like these minor differences. And of course, like the diagram always helps you to have a better understanding. Like the top example that Nick mentioned, like it's like you're applying single ones on each one, and then the second example is actually the circuit that we call as a Fourier transform.
Three-dimensional one.
It's still like it's still interpret that as operator, I guess, there, if you do not use composition. Yeah.
Actually.
Unless you wrap it around quantum circuit operator. Yeah, that's another way of doing that. Yep. So circuit inside circuit, or a composition of circuits, like it's just different way of constructing a very complicated. And the last example, like this is the last example that we had prepared for today. Let's say that like I meant Bell circuit. So Bell circuit, yeah, it's Bell circuit followed by quantum channel of bit flip P1, which goes on the first one, and then we have quantum channel so that's what we have here.
Besides this label.
Yeah, the label, like I make a note of that. Like when it's not one, the label kind of acting crazy. So of course, remember that like the quantum channel is basically describing the effect of the noise on your system. So that's how we can include it.
Yeah, quantum channel is a bit raw operation at the moment.
Mm-hmm.
Especially when you compile a circuit with quantum channels inside of it, using tensor network.
What else? I'm thinking like, what other interesting features would you like to comment on like the one that we discussed yesterday regarding like quantum measurements
and POVMs?
Yep.
Oh, sure.
Because nowadays, like it's
Or maybe in general, how every object is related to each other.
Yes, that's yeah. How nesting is done, that's also interesting.
Because we haven't finished discussing this last time. Right?
Yes. So, let's discuss that
one. So the most elementary thing in the framework is names of qubits. Right? Maybe you've seen those. This is just names. They don't have any semantic meanings. Right? Those are usually just seen in the formula. Right? The next thing that we have is a qubit basis, which is basically the name or names with some numeric representations. Like if you make a qubit basis, usual one for the qubit, out inside of it is just a list of representations like this. Right? So you have this 0 ket on the first qubit and some representation, usually some vector 0, 1, and normal. It's like 0, 1 representation, and ket number 1 has an orthogonal to that representation. Okay, so this is how qubit bases are represented, and it's this kind of association of representations with names and nothing else. Another step in the abstraction is quantum bases. There we have. This is basically a bunch of qubit bases and some meta information, like pictures and so on. For example, quantum bases, usual quantum basis for a state, for a single qubit state, contains an output qubit basis, which is the one, exactly the one that I showed you above, and the input one is just a one-dimensional qubit basis with no qubits, right? But so it's you can't say that there is no input. You can only say that it's just one-dimensional input. It just doesn't take anything. Okay, so that's what quantum basis of a quantum state is, for example. And it also contains some meta information like labels, and by default it's none. Some picture, which is just usually not used at all, but we just have it in case we're gonna need it soon in the future. We actually have some plans in order to use those, especially for phase space representation. And maybe what else does it have? Oh, like parameters, but we haven't showed them yet. So this is the quantum basis. It's just the most essential part is that it contains two QGT bases for output and input. Okay, next step in this hierarchy of presentations and abstractions is the quantum state. It's a bit more general than just quantum states in the usual case. So if you construct a quantum state like this one for a single qubit, right? Underneath it is just this list of amplitudes and the quantum basis, nothing else. So it also has a basis like that, exactly the one like this one basis or here, and the list of amplitudes, or maybe we'll call it just a state vector, right? Which is a sparse array. In this case, it just contains A and B as an element. And this is the quantum state when it's of type vector. But you also can make a different quantum state of type matrix, right? Which is also has the same exact representation. The only difference is that instead of a list of amplitudes as a state vector, it has a density matrix. But it also contains the same exact quantum basis underneath, right? So, all right, now what? Now we have a next thing ahead or above it is quantum operators, right? And the quantum operators is actually this particular quantum state, because it's very general. The basis can actually have a different outputs and different inputs. Dimensionality on those are different, can be different. So quantum operator underneath actually contains a state, right? And in this case, it's a little bit more general than the usual state. It's a pure map. So now it has an output dimension. If you ask for an input basis, now it also has a two-dimensional input with one qubit in it. So that's the main difference for the usual operators. Now, its input basis is not one-dimensional as for the state, but it's two-dimensional. And then also, so basically, quantum operator is a state, and one additional thing the quantum operator has is an order. So you can think of an operator as a quantum state, or this general quantum state version with an order. And an order allows for quantum operator to be essentially a quantum gate. So you can, without modifying a tensor or underlying state in any way or basis, you can put it anywhere on your circuit. You just specify an order, and it's very easy modification of quantum operator. You just change its order and nothing else. All right, so that's the quantum operator. It's a quantum state passcode.
Nick, show like the 2 qubit, for example, C naught. Show the order for the C naught, just as another example.
2 qubit operation, it's going to have an output order and an input order. So you can even change one of them. It's not going to be well represented in the circuit layout, but in general, if you have like this qubit, this operator, two qubit operator, you can in general even change only one of them. Like you can change 3, 4 as an output and 10 and 20 as an input. Right? So now it's like an operator that acts on a two qubits on wire number 10 and wire number 20 and outputs on the completely two different qubits. So you can have objects like that, but you don't have like support for them in the diagram of a circuit, but you can
Yep.
work with them by just composing them together.
But so like one interesting take-home lesson for our students is that like although the typical conventional diagram and the wires is a very good language or metadata to understand what's happening with quantum operations, quantum transformation in general, but remember it has also many limitations. For example, in our framework, like this very last example that Nick is showing you, like you could have some very interesting features, very useful for some like very nifty computation, but practically there is no nice representation using the diagram. Okay, so that's like one of the headaches of like dealing with the only diagram. So one thing that I always tell a student is that diagram very interesting. Like I know, especially among computer scientists, they love it and like and they work with it a lot. But if you are like pure quantum researchers, this is one of the many options, and it doesn't include everything. So keep that in mind whenever you are working with quantum diagram.
Yeah. Okay. So, and basically here I've just showed that you can compose different things. So if you have output on the third qubit, and fourth qubit, but your another operator that you're composing it with has a different order, it's going to add it appropriately, so it expands the operator. But if it's on this acting on the same qubit that already had part of an output, well, it just acts it naturally. So now it's the same dimensionality of a tensor. But
By the
nothing
way,
changed.
Nick, these two examples, can we like the difference between them? Does it reflect on the tensor network of the corresponding like circuit? I never think about that. Like, so just do you have any thought on that?
Well, you can't really put it in the circuit normally. I don't guarantee how the circuit gonna behave if you have these weird operators in different input and outputs. So
Okay.
I can't really speak to that. It's like very
So as of now, like the tensor network for us is only when like we wrap it around properly as a quantum tensor, as a quantum circuit operator, right? We do not have tensor network only when we have operators like this.
well. I don't know. Let's just be dangerous and see what happens. Okay, if you actually have a quantum operator with this list
Yep.
of tensors here,
Yep.
instead of applying them, composing them on the spot, let's see. Well, let's see what's gonna happen. Probably not a correct diagram because
Uh-huh.
it's basically doing something weird. But maybe tensor network is somewhat meaningful. Actually,
And
with
then the
the
yep,
indices,
yep, yep.
tensor network index graph. Oh wow! Kind of
Okay.
expanded it. It's very big tensor, so it actually made it
Up
up
to
to the 20, up to 20.
20. Yeah.
Yeah,
Yeah.
it makes it complete.
Okay. So at least like we see that, and if you let's look at another tensor, and this time let's have Pauli only on the first one. I guess like then we would be able, at least at this metadata level, we can see the difference kind of. Yep.
It only will be
Yeah, yeah.
visible on the index here, where it contracts in a different position.
Okay.
I think it doesn't really create this giant tensor in memory. It just
Mhm.
creates the indices. So that's it.
Okay, for some quantum states, like and the quantum operator, show the arity. Like we never discuss about that.
The arity just means like property arity. It's almost the same as width. It's just if you have a operator acting on some order that skips a bunch of qubits, you're gonna maintain the arity, but the width is gonna be 4. So arity is basically the length of the input. So if the wires are not occupied, it takes it into account. But the width is the maximum. Okay. I want to continue on this.
Yes, please.
Abstraction ladder. So we ended up on the operator. Now the next one obviously is the measurement one, right? So the measurement operators in this abstraction ladder is basically an operator, but it has some information about what we're actually measuring, and it's nothing else. It's just something like another order, but we call it a target. So it's like a measurement target, basically. Underneath it's still some quantum operator, right? Which we know already that it's some kind of quantum state with order, but quantum measurement operator is an operator with target. Okay, so nothing else. And for example, if your quantum measurement is turned into POVM1, so that it's like this signature is not square anymore but rectangular, which also means that its diagram has an additional output. Basically means that its underlying quantum operator has an output with two qubits as an output, and we use as a convention this non-positive qubits in the order as some special qubits, like in the case of a measurement, it's where we put our targets. And also in the case of a channel, which is also basically the same as quantum measurement operator in the PVM case. So like if you have a quantum channel, it also is just a quantum measurement operator. It's also quantum operator even without any target specified. It's basically just a quantum operator. It's only difference is how it composes with other stuff.
And does it always happen whenever we have those, super operators?
Yeah. So if you POVM is basically a super operator. So if you convert, if your POVM measurement is what we call a super operator, so this is going to be a corresponding super operator for this measurement operator. So yeah. So this is like an extra qubit. Because by default, by convention, is not positive. If you measure like 2 qubits instead, now this extra qubit is 4-dimensional, and what we were showing you previously. If you do it differently, if you actually compose 2 measurement operators instead, like that maybe, right? This differs by the number of qubits. Instead of creating 1 extra qubit, but it's 4-dimensional, now it's 4. Now it's 2 extra qubits, but still of the same dimension. So this is like the difference between those, but semantics is the same. If you actually want to extract probabilities and so on, or maybe change your basis.
The extra ones, like for our students, we always add them to the left. So like it's gonna be 0, -1, and it goes that's how.
But convention we add them to the left because it makes sense. If you have normal qubits as a positive number going 1, 2, 3, 4, it's much easier to make to go on the other direction instead of just adding them those classical bits to the right. So that's why we like in our measurement or with our measurement and circuit diagrams to have a classical wire on top, because it's kind of, if you read it on the left, if you turn it on the side clockwise, it's on the left of all the other qubits. So this classical wire has index 0, -1, -2, depending on how many measurements you performed. So that's the explanation why we like this convention more.
Yeah. And this is also related. You guys remember, like, we had that discussion, like, whenever we have a measurements, we go to higher dimensions and, like, we do some fancy things. So that's kind of like, another way of, looking those as those higher dimension, because when we do that, like, there are tons of interesting information that we can save spatially for future operations. Otherwise, like, you're gonna have a big headache if you want to do, like, some future operation on the top of your results.
This basically this holds for channels too. It's also a quantum operator with an additional output.
Hmm.
So those are the quantum channels. And I guess what's left is quantum measurement. Is when you measure stuff, you usually get this quantum measurement object, and underneath it also have no more additional information that quantum measurement operators already have. So underneath is just if you ask for a quantum operator, it returns a measurement operator, but the POVM one, but it has no output. So basically the measurement object that we have is this weird measurement operator with no inputs, right? So it's all the inputs is one dimensional input. It also has this special classical qubit or qubit, which is 0, -1, and so on, but has no inputs. So this is how we treat measurements. And all the information about probabilities, post-measurement states, and other properties of quantum measurement can be extracted from this measurement operator as a tensor with this particular dimensionality and orderings. And I guess this, and the quantum circuit operator is, you already know, is just a list of operators and nothing else. And I guess this concludes all of this abstraction layering.
Thanks, Nick. So, like, it's uh I know it's maybe too much, but, like, this development, it went through, like, the lots of iteration, and what you see here is the big overhaul that Nick did to have a sort of, like, a unifying metadata to address many different things that can happen, like, in quantum, from measurement to, like, usual unitaries to this, super operators, each case, like, fancy case, and, like, uh, in order, like, this language, this metadata helps us to unify all of them together. uh, those of you, again, as I said, having a kind of, like, a knowledge of, like, what's happening behind the scene, definitely very useful. But the way that we design our framework, you don't need that knowledge at all when you're working with our framework. Like, it's exactly the usual approach that we have in quantum theory. Like, you apply operators on quantum state, you get another quantum state, you do this measurement, you are going to get, a bunch of probabilities, you do quantum channeling, so, like, you're going to get a, like, a mixed state, etc. So that's how it works. There is a question by Mike. uh, so basically, like, whenever we are using, a prefix, that add sign, like, we call it compose, and when we have, like, composition, we also call it um uh
Oh, it's kind of similar. If you use just the add sign, basically mean compose function with some argument, right? It's kind of
mhm,
also can be called compose. Maybe it's not correct to call it,
yeah,
but we kind of mean it in this way. We can, when we compose an object, independent of their nature, how we apply them together
yeah,
to make some new object.
yeah, like, Mark, like, if you want to be very picky and following the Wolfram language, like, terminologies, that add sign, we should not call it compose, but then it's going to be very confusing how to explain that. So, action of an operator, an operation, I don't know what is the best way of, describing that. But you are right, like, composition, and I guess, that's one of the reasons that, like, it's called composition in Wolfram language. So maybe, let's see, do we have?
Composition is usually called this thing.
Yeah. So like, you know, so we don't have like, actually there is no compose. I felt like I just checked that. I was not sure, like, you know, we don't
I
have.
don't think those are just compose.
Yeah.
This is just, I think it's some weird old version of composition.
Yeah, since version 2, like compose, you know, it has been, you know, superseded by composition.
Yeah, it's an old
So
version of composition.
version 2. I wouldn't mark if you have been using in a Wolfram language since version 2. Like I know you are
works,
one of our power users.
kind
So,
of. It actually immediately acts as apply.
yeah.
So in this sense, it's the same as this. So in this sense, it's correct to call it a compose. It's weird.
But like, you know, yeah, it's maybe apply is the closest, you know, you know, very, you know, the closest to Wolfram language. We should call it apply. But like, you know, that's interesting because
No,
most of,
apply is also incorrect. Apply
yeah,
is
because it has like apply has a complete like it's different. So
it's usually, I think, the construct.
yeah, even the syntax is different for apply. Is it construct or?
Apply is just by default without anything else. So it's not going to work in this case. So you see, it kind of destroys it. It changes the head. That's the idea. It destroys this head, replaces. That's what apply is doing.
So that I guess, Mike, that's why, you know, we had a hard time. You noticed that correctly. So we call it composition mostly for, you know, these purposes that Nick explained here. I think, you know, we can wrap up our study group. It was fun. We learned a lot every time that we are interacting with you guys. Like, you know, we learn a lot. Let us know what you think, like, you know, how you are using our framework. You know, if you notice anything, like, you know, you can contact us, quantum@wolfram.com. You can comment on the community through Wolfram. You, whatever guys you are more comfortable with, like, you know, let us know your thoughts. You know, we would be happy to offer, you know, more trainings. Some of you, if you are in academia and if you would like, you know, some training for your students, please let us know. You know, we can also offer, you know, those particular trainings. And, you know, just diving and explore our framework, and let's see, you know, how we can contribute to this, you know, big third quantum revolution. So the first one was the beginning of quantum. The second one was like, you know, the research on foundation by people like, you know, John Bell and others. And the third one is technological, you know, development using quantum technology. So thanks everyone. Thanks Nick. Thanks Cassidy for your help. And thanks everyone for attending this series.
Thanks everyone.